Byron College, a British international school tucked away in the suburbs of Athens. We have kids from years nursery reception all the way up to year 12, and from 40 different nations. Enjoy the video.
Such a body of large mass and small size, which has a singularity in its center, is known as a black hole. Black holes are created when a star collapses in on itself. Stars form by the collection of gas particles, which slowly accumulate due to the gravitational effects. When the particles are densely accumulated, they collide with each other at high speeds and create a lot of heat energy, which eventually allows for hydrogen atoms to combine and form helium in a process known as nuclear fusion. This is a continuous process, and the outward pressure created by this acts as a resistive force to the gravitational force caused by the mass of the star as it acts inwards. However, at some point in a star's life, the fuel, primarily hydrogen, runs out, and at that point there is no resistive force that acts against gravity, and the star begins to collapse. The star can settle to a white dwarf or neutron star without becoming a black hole, but if the mass of the star in relation to its radius exceeded a certain point, the Schwarzschild radius, the star is bound to collapse in on itself. Applying the formula for the gravitational field of an object, it is clear that the gravitational field is inversely proportional to the radius, while the mass is directly proportional to it. Thus, a body of large mass and small radius will have a very large gravitational field, large enough to not allow light to travel out of it, and thus rendering the body into a black hole. Thus, according to the special theory of relativity, since nothing can travel faster than the speed of light, then nothing should be able to escape a black hole. However, something funny occurs when you don't feed a black hole. Eventually, it evaporates. This process of evaporation is known as Hawking radiation. Quantum mechanics allows for the spontaneous creation of virtual particle-antiparticle pairs. Particle-antiparticle pairs form near the event horizon of a black hole, and thus one particle enters the black hole while the other travels off into infinity, thus emitting radiation. However, this would contradict the principle of conservation of energy. No energy can be created or destroyed, so the conclusion that the black holes evaporate is reached. This is explained by the fact that real particles always have positive energy. Thus, in the particle-antiparticle pair, where one particle has negative energy and the other positive, the one with the negative energy, being virtual, will fall into the black hole. According to Einstein's equation E equals mc squared, negative energy will correspond to negative mass. As a black hole receives negative energy, its mass will decrease, causing it to eventually evaporate.